Cool, and we are live to the large internet, to anyone who wants to be listening. Hey, I am Callum, here to talk about the application blockchain interface, which some of you might know, some of you may have no idea about. I'm just hoping to, in the end, sort of enlighten all of you, because there are some very exciting changes happening to this in the sort of next release of Tendermint. And I think it's something that a lot of the wider audience is sort of excited to actually understand what that really means. So this talk today is going to sort of cover about these sort of changes and what that sort of unlocks for application developers, people building on the Cosmos SDK, people building directly on top of Tendermint. Before we sort of get started, I'll give a quick introduction of myself. So my name is Callum, as you can probably tell. I sort of joined Interchain 2 years ago as a software developer working directly on Tendermint. I have sort of been in and amongst a lot of the code, ranging from like the evidence stuff to light clients, even to the consensus. And more recently, I've sort of now taken the role as the engineering manager. So managing a sort of team of, it's about 5 or 6 of us that work full time on the Tendermint core. And for those of you that sort of know Cosmos SDK or know the Cosmos ecosystem, the Tendermint is like the lowest in the stack. So it's the thing that does the consensus and the networking. It's the thing that makes sure that your application state gets replicated across all these nodes and in a way that is Byzantine fault tolerant. And so a little bit more about the Interchain. So this is the sort of company that works on all the core infrastructure. So you have a lot of ecosystems that build applications, and there's different parts and whatnot. And Interchain Foundation is the one where a lot of the funding for these projects comes from. And then Interchain GmbH, which is more the like operating arm, is where all the sort of core infrastructure gets worked on. So we have teams working on the sort of IBC is a big one that a lot of you might be aware of. And Tendermint, we have teams working on the Cosmos Hub. And also we have a lot of involvement in the SDK. One of the newest things that we actually have also is like a builders team, which is to sort of like bring all these people who are building on top of that sort of core infrastructure sort of closer to these developers and sort of have a sort of closer relationship. Anyway, let me sort of dive into this application blockchain interface. So for those of you who don't know, you might have sort of experienced working on other sort of networks, and they sort of combine all the sort of business logic, the consensus, and the networking all together. So if we sort of take a brief history of like the Tendermint and the Cosmos ecosystem, we sort of came across this like separation of concerns early on, which I think was a quite pivotal step in the sort of growth of the Cosmos ecosystem, where we sort of realized that you have a consensus engine which only needs to ensure that a group of participants can all agree on a set of state transitions and update state accordingly. It doesn't really need to know what that state is, nor what's in those transactions, only such that everyone that's involved have some sort of algorithm and protocol which we can agree on it. And the application itself, they only need to ensure that there is deterministic business logic. So they're the ones that can decide those transactions, and they can rely on consensus to make sure that those transactions will get executed and that everyone will have an agreement of the state. So in many other sort of networks, those things are sort of merged together, but we sort of came along this idea that they're actually quite separate, and it does make sense to have some sort of like interface between those and to have those as two different things. And this is what then gave birth to ABCI, which is the application blockchain interface. And this interface has been around since the sort of start of Tendermint. You could go as far back as like 2014, 2015, when it was initially getting written. And then we had that sort of like separation. And what that interface consists of is these like 4 connections. So there's 4 places in which Tendermint, which is the client, creates a call to the application, which is the server. And so just to give like a little bit higher context, when I say application, quite often that means the Cosmos SDK, which kind of is built on top of it, and then whatever sort of modules that consists of, and then that collection of modules then sort of makes up your application, whether it's Terra or Osmosis or the Cosmos Hub. And so going back, we have these like 4 connections, and the first of which, and the main one, of course, is consensus. And consensus consists of a couple of calls that it makes. And we have these like kind of separation of, the whole voting consensus phase, where the proposals, the blocks are propagated, the votes are sort of made and propagated around the network. And then also there's this protocol that once you reach 2/3 of this voting, that we sort of execute on it. And once we execute it, we sort of do this in like a very like serialized order, which we have begin block, which just sends the header, any evidence that was sort of committed, and then sort of like what the sort of consensus params and stuff are. And then we have to deliver to TX. So for every single transaction in a serialized fashion, we'll take that transaction and send it to the application, and then the application will return any events, which then get emitted. You know, if you're using Postgres or something like this, you can then sort of listen on these events and run something on sort of indexer on top of that. And then finally, we end with this end block, and the end block is the opportunity to then sort of submit any validator set updates, any consensus param updates, any other sort of events that are just related to the end block itself. Quite often, a lot of modules will be written so that logic that is dependent on the height or dependent on time or just happens for every block gets executed. So it's not just transactions themselves that cause state transitions, but also just the fact of that block. And then finally, we have the commit, which is, okay, this is now set in stone, and the application can persist that new state to disk. So that was the existing calls and consensus. We also have the mempool. So the mempool is that sort of in-memory pool, I guess, which takes all those transactions, gossips them around beforehand, and then when it comes to the proposer wanting to be able to propose a block, they reach into their mempool and grab those transactions. And the mempool has kind of like a soft check for any transaction coming into the pool. So anything that comes in, it will go to the application and be like, hey, is this okay? And quite often when I say soft check is because there is some time between, there could be many blocks theoretically executed between when a transaction comes into the mempool and when it actually gets finalized. You can't actually be sure that that actual transaction is valid, and there hasn't been some sort of state transitions in between that have made it invalid. So quite often what checkTX is used, and in the case of the Cosmos SDK as well, is just like a validity, like a really basic validity check, so that the structure is correct, that perhaps the account sequence is right, and whatnot. And if not, then it gets sort of evicted from the mempool. If so, then it gets passed around, and eventually, hopefully, it gets put into a block. The next connection is state sync. So state sync is a sort of new method that was introduced, or like new sort of protocol that was introduced in 034, which is quite exciting. Previously, if you wanted to start your validator and the chain was already at height 1 million or height 10 million, you'd have to do what's known as like block sync, or some people call it as fast sync, although perhaps not as fast as state sync, so a bit confusing, where you would take every single block, you'd sort of query every block from pairs, and you would validate every single block as it happened, and then execute that block against the application and get those sort of updates. So this means you had to go through all 1 million blocks in order to get to the head of the blockchain. Whereas state sync uses the sort of light client verification, where it can just verify a couple of headers at a time, or like it kind of can skip through, so it can verify header 100 to 200 all the way up to the head of the chain. So it knows what the state at the head of the chain should be. And then instead of just having to sync through all the blocks, the applications gossip the state between them. And you'll see this in the calls they have. So you have these like snapshots that you can list, and then you can offer a snapshot to the application. If the application accepts it, then you start sending these chunks. The state of the application gets chunked, and then you apply them to your application, which is trying to like load its state, so to speak. And then once that's happened, it can then sort of move on to participating consensus. So that's one aspect. And then the last connection is just a simple like info. And this includes a lot of like stuff needed in the handshake. So whenever Tendermint starts up, it wants to make sure, hey, application, what state are you in? And what state do you need to get into if I need to replay any blocks because you've lost something? It's used for querying, which is part of the RPC. And then you have like Interchain, which is for basically initializing, it's called once upon startup. So those are the 4 existing connections of the legacy interface. The thing that we're sort of focusing the most with this ABCI++, the sort of most important part of it is consensus itself. So these sort of 4 calls have been sort of modified, and I'm now sort of going to explain how that happens. Before we sort of get this, I want to talk a little bit about sequencing. I think it's like kind of important. So currently Tendermint has what I would call delayed agreement. Some people call it delayed execution. I guess the nomenclature can sort of vary a little bit. But the way it works is that a proposal will propose and the validators will agree on a set of transactions. Once that agreement is made, each of those validators or full nodes will then send that to the application to update their state. So then you have execution. after execution, the hash, which derives of like what that actual state is, gets returned. And that hash only gets then put in the following block. And the hash is then what is used to verify that all those participants have reached the same state. So in a sense, you don't know what, that all the sets of transactions are the same and deterministic for each application, but you don't actually know that you've all executed in the same way and reached the same state and effectively done state machine replication until the following block. So in this example here, you have block 100, and that has a whole bunch of transactions, and you execute on state 100. And then that state that is created is only agreed upon in block 101. So in block 101, that'll include the hash of state 100. And once we agree on block 101, which is, as far as the application is concerned, state 101, where we actually know that state 100 was actually like replicated and there wasn't any like non-deterministic failure, where like some people got this app hash and some people got this app hash and we couldn't reach an agreement. And what this also means is that like you have a whole lot of these off by one errors, because the block, like for example, any of these updates. So if you update the consensus params, you change the size of a block, or you want to change how many, any of these things. Also what the validator set consists of, if you want to add more validators or you want to change their voting power, that actually doesn't happen until 2 blocks afterwards. So not just the next block do those changes come into play, but the block afterwards. So this can also be a little bit confusing for developers to work on. So this is what's currently is delayed agreement. And there is another way of doing this, which is known as immediate agreement. And the order which this happens is that first you have a proposer proposes a set of transactions. Then when the proposer then gossips that proposal, each of those participants verifies that they have the same state. So they quite often will execute those transactions, verify that they have the same state, and then agreement comes afterwards. So I think another way you can sort of call it is like speculative execution. So you're like speculating that this will be the block that we agree on, and then we can already like execute those transactions. And then it's just about making sure that, okay, have you got the same app hash as I do? And what this means is that you can have all this agreement in the same block. It makes it a lot easier for developers to understand, because it means the next block is the one that, those validate updates or consensus param updates will happen. So this is an important thing because this relates to ABCI Plus, and I'm going to sort of explain a little bit more detail. But essentially, ABCI Plus allows for both of these things to happen, or for application developers to choose whether they want immediate agreement or delayed agreement. So let's just wrap up this like legacy ABCI by like going through what are the sort of current pitfalls. So the main thing is there's no filtering of bad transactions. There is nothing stopping a proposer from putting absolute garbage as transactions. And because Tendermint has no knowledge of what those transactions are, it will still agree on we'll still get the same agreement on what garbage. But when it comes to then being executed to the application, which happens afterwards, the application is going to be like, well, I can't do anything with this, and I'm just going to keep the same state I had afterwards. So there's no as I said, filtering of bad transactions. The next thing is that there's no room for concurrency. So, and this was like more of a design decision rather than like a fallback, which is when Tendermint was first being designed, it was done in a very defensive way. And the way this was sort of achieved by making everything very serialized. So you couldn't sort of like execute things concurrently. Each block was given, like each transaction, as I said beforehand, was given independently one after the other in the order that it was received, to make sure that there was no sort of problems with the app hash, to kind of reduce the chance that the application would have misprogrammed their state machine and you would have had this like non-deterministic app hash. And the last thing is that it just gave less control to applications. And this is going to be seen more apparent later on, but the whole idea was with this creating this like interface, as I said, was done as a very defensive way and didn't really allow the application to like really take full control of consensus. It kind of said, like, this is the way we expect you to behave, and you have no other choice but to do this. So let's move on to the ABCI Plus, or releasing the Kraken. Like essentially what we've done with a lot of the sort of work in Tendermint is kind of unlock everything, allow the application far more control over what's actually happening in consensus, and to be able to then reap a lot of the benefits from that, as I sort of explained now. So let's take a high level glance of this. So take those like 4 calls that you had beforehand and sort of like put them to one side. So these are like what the new consensus connection ABCI calls look like. So you have Tendermint in the bottom and then the application on top, and you have these 4 calls. And instead of them being grouped right at the end, so you had begin block, deliver TX, end block, and then commit, and that were all done just together. Like Tendermint did nothing in between. These calls are done like during consensus and throughout different aspects of consensus. So you'll have prepare proposal, which gets done before the proposal even gets sent out to the rest of the nodes, so it gets propagated by the network. And that allows the application to then sort of choose what sort of transactions they want and ordering, and I'll get to this more. You have then the proposal. So in between, once Tendermint has the proposal, it then gossips this out to the rest of the network. And then each node that receives it then has this process proposal phase. So before we even get into voting, as like a precursor, now applications now have the ability to check what is actually going to be in a block. And with this check, we can actually make sure that like every block is valid and contains only valid transactions, because anything that's invalid, it's not going to agree on. And then whatever the application returns, Tendermint will then sort of pre-vote and pre-commit accordingly. So if it's not a great block, it'll pre-vote null. The last one is like extending the ability to extend votes. So this now allows arbitrary data to be put in the votes themselves and signed by those validators. And then the final thing, which is kind of an encapsulation of all those previous calls, is this finalized block. And I'm now going to sort of just jump into each of these to explain them a little bit more. So first off, we have preparing the proposal. So whereas beforehand, this was done purely by Tendermint, it would just grab the transactions from the mempool and then just fire them throughout the rest of the network. You now have this like call that it's made to the application. And what that means is, getting a little bit of delay here. And what this means is that, so you have transactions from the mempool are batched together and given to the application. Once again, one of the new things that has been introduced in Tendermint is a prioritized mempool. So applications can now choose the priority with which transactions arrive. So beforehand, it was just FIFO. So whoever delivers that transaction first to the network is generally the first that then comes into a block. But now the mempool is able to prioritize things. Quite often this is used based on like fees and stuff, but it allows for like greater economic mechanisms in choosing which sort of transactions make it through. Anyway, that those top priority transactions get sent to the application, and the application can then go and like manipulate this. So it's able to add their own transactions. So there are examples of networks that want to add intermediate state proofs, or I don't know, any other sort of like transactions which aren't gossiped in the mempool, but perhaps are a byproduct of some of those transactions that actually happened in the mempool or a previous state. So now they can add their own transactions. What this current also means in a way is that if they want to have another process that sort of complements the mempool that also does transactioning, there are examples of networks that want to have like some sort of like bartering that agree on prices beforehand. Then they can sort of do this, and then the application can then sort of add these transactions when it comes to prepare proposal. Of course, like the big thing is to be able to remove transactions. Anything that is now invalid because of previous transactions or previous state transitions can be removed. What's more is you can merge transactions. So if, for example, there are transactions by the same sender, multiple different ones, they can be sort of grouped together. Or if they're, any sort of other thing, you could sort of have some sort of signature aggregation or some sort of way of like making these transactions more efficient. So you can also merge them. And lastly, which is also quite important as well, is the ability to like reorder transactions. There is a lot of like, if you sort of worked in sort of the DeFi area, there's a lot of talk about front running and all that sort of stuff. And by giving applications control, you can actually not only like reorder transactions in a way that might be opaque to the proposer, and so that which they cannot they sort of manipulate them. But with the next sort of call that I'm going to go to, process proposal, you can ensure that like you sort of kind of have the tools to be able to ensure that there hasn't been any sort of manipulation in the mempool. Cool. So now a few other things about preparing proposal. So once that gets sent up to the application sort of runs this and then sort of returns that sort of data. And then so it takes those sort of new transactions, and it adds the header, evidence, and sort of the last commits, which are the existing stuff in the block, and then begins gossiping this. There is a case for immediate agreement. So as I said before, ABCI Plus supports both delayed and immediate agreement. And in the case of immediate agreement, actually in that prepare proposal, you want to actually return whatever sort of param updates or validator updates, as well as the new app hash. And that will then get formed in the header along with the block and sent across. So basically what's saying is like, if we agree on this block, these are the updates that are going to happen. This is the app hash that you should get. And so when that gets sent out, that's how they'll process it. So processing the proposal is pretty simple. Once that proposer has gossiped it out to each validator, they do their Tendermint checks, which is to check for, check the evidence, check the header, check a whole bunch of state transition, like Tendermint specific stuff has happened. And then whilst that's happening, they can also send it up to the application to make their validity checks on the actual block data. And so essentially, they're allowed to validate the proposal. And so if there are any invalid proposals, then the application has the ability to say like, no, don't vote on this. So vote nil, and the consensus votes nil on this, then it'll move to the next round, and the next proposal will have the opportunity to propose a different block. And eventually you would want to find a block that is valid. Okay, one of the most interesting things and gets really into sort of the consensus is this idea of extending votes. So essentially you have in Tendermint 2 phases of voting. You have a pre-vote and a pre-commit. The pre-vote is essentially to decide which block of all the blocks that can happen in every single round should we lock onto. And then the pre-commit is like, okay, which one should we actually commit on? And once we get 2/3 of both of those, we have actually like finalized that block. So extending votes is something that happens in the pre-commits only. And essentially what it allows is the application can now allow each validator in the network to directly add transactions to their votes. Beforehand, it's just the proposer that chooses the transactions and accumulates them together. Now each validator can sort of like add transactions by signing them alongside the vote. So you have the vote, which includes, the round, the block ID that they're signing for, and all this other sort of information. And then there's like signature, so that the validator uses their private key to sign. And not only will they be signing this vote itself, but also these extensions, which can just be sort of any arbitrary bytes, the same as like a block. And so what happens is that these will be signed by the validators, and they'll be verified. And if they are verified, then the proposer of the next block will include those votes with the extensions. And so what happens is that those can be executed in the following block. And this is really good for stuff like price oracles. So you can have each of the validators be sort of, in a way, sort of like querying, different sources and returning like what their price is for something. And then you can then take it in the following round, take all those transactions that each of the validators signed and work out what the actual price of something is. There's a lot of other things like in terms of signature aggregation and whatnot. But I guess this gets more into the technical realm. The last aspect is finalizing the block. And as I said beforehand, we had all these like individual calls. Now we're sort of trusting the application to be able to handle this correctly. And so what we do is we just provide the block in its entirety. And what this allows is for concurrent execution. So instead of getting the transactions in the order that they come, you could actually sort of group the transactions by which part of the state machine they affect, and then execute those in a sort of concurrent fashion. In the case of an immediate agreement, the state has already been executed, as it would have done in prepare proposal and process proposal. And so therefore, this sort of final call is just to acknowledge that that state has been finalized. So those are the sort of like 4 method calls. There is another aspect as well that we're changing with ABCI Plus, which is the entire sort of like concurrency model. So for a lot of like, especially like local clients, and this was part of the whole sort of like defensive programming around Tendermint, is that basically Tendermint held a mutex around the application, or at least around the ABCI, which meant that calls could only be done serialized. So if you're doing a check TX, you have to wait for that check TX to finish before Tendermint would then send the deliver TX or send the commit and stuff like that. So it could only be done one at a time. A lot of the decision, like the thinking behind this is that, well, that should really be up to the application to decide, and they should be responsible for it. In the simplest of cases, the application just implements that same mutex on their side and has that same thing on each call. Or if they want to, they can try sort of, as I say, batch different parts of the state and form some sort of concurrency, especially with like reads and writes. So like especially if check-tx is just a soft check on state. Maybe you can still be able to run check-tx's in parallel with different parts of the consensus connection. Cool. That sort of rounds up the sort of like half an hour I was planning on talking about this. I guess I've sort of blitzed through it quite quickly, and there might be a lot of things that you have different sort of ideas or coming in with different contexts. And so I'd be happy to sort of answer any questions that people might have now. I guess it was more comprehensive than what I thought. Yeah, so that, yeah, just so that people know, there is this like chat to the right, and I'm just looking at this. Or if you've, yeah, something you want to say, you can sort of raise a hand. Yeah, if you got anything else that you're interested in listening to, we do have a GitHub, so Tendermint, and there's the Tendermint spec, and a lot of that sort of has a more of a deep dive into what ABCI Plus looks for. This is something that's going to be coming out in the next release, so in 036, which will then sort of move into the Cosmos SDK. And there's a lot of work currently about how the Cosmos SDK can unlock a lot of the ABCI Plus to improve their, stuff like performance, or just to add more functionality to what module writers can do. Just hold on, I'll do this one at a time. Is this a module that needs to be added to your chain, or is it implemented into the SDK? So this is directly in Tendermint, which is kind of what SDK then imports on. So this is something you sort of just get out of the box. So this isn't not necessarily something you'll need to be able to implement. It'll already be part of it, which is the kind of the great thing. Like a lot of these sort of changes, you kind of get it, without having to worry about it. One of the questions that a lot of people ask who are building modules is like, is this a breaking change? Will this break my current module implementation? What this will do is it'll add potentially methods, which you can just have them as a no-op, so it doesn't really have to be breaking. Yeah. This is, Damien, it's a very interesting question. I think the first thing is that the SDK will go with more of a naive approach, which they will sort of, they will do the whole like concurrency stuff and execute the mutex around each of these calls. I would be interested to see how this develops. It can be a very like difficult challenge, but you could essentially have some degree of like taking those transactions and then looking at, especially if like transactions only affect a module and don't have any dependencies cross with other modules, and just being able to execute those and give them to their module to handle. Does that sort of like answer both your guys' questions? Cool. This is an interesting experience. All right, I guess I'll wrap it up at that. Thank you guys for joining. And yeah, all the best.